peek at my emails just to make sure nothing's coming through there. Doesn't look like anybody's rattling my chains there. Well, why don't we go ahead and get started? If all else fails, there's always the recording for folks to rely on. So, as I mentioned in the email, this will be our last session. I'm going to go through a couple of topics here, though mainly going to be looking at combining individual data with the aggregate data, and at least one approach for dealing with that. So that'll be the bulk of the time. I should also mention that for those of you who do want to get a certificate for this and are taking, in other words, taking it for credit, I need to put together the final. Actually, I think the final will be an extension of what we'll talk about today. It'll actually be doing some work with the results of the excuse me while I try and figure out why do I get dings here. Excuse me. Anyway, let me continue the thought. I think it'll be a continuation of the example I'll show you today. So I'll give you some inklings of what the final will be, but I'll actually write something out and post it probably by the end of this week here. So let's go ahead and get started on some of the material. Again, let me see if somebody's sending me messages. No, I don't see any messages. Trying to figure out what's going ding on my computer, and I'm not sure what it is. Okay, I guess I don't know. We'll just leave it at that. Okay, let's start out briefly with one topic I'll just mention that comes up when working with aggregate data from published sources, particularly, is this aggregate data, or the summary statistics that we get, tend to be things, are summaries of data, most often treatment means, which are, there goes again. Still not, oh, maybe that is people joining us. Okay. Are often, hello?
Yeah, this is Dana. I'm just wondering, I went to the GoToMeeting. Do you have something up there? Because all I'm seeing is GoToMeeting, beginning screen. There's no content or anything.
Let's see. Supposedly, it's showing my screen. Let's see. Hopefully, it's not just being terribly
I see
slow.
your screen, Dale.
You do? Okay. And that was Dana. Are you seeing anything yet?
No, let me try it again here and see what happens. No, I'm just getting the GoToMeeting screen.
Is anybody else having that difficulty? Okay, Mike is saying he said he had to reinstall GoToMeeting for some reason. Are any others having difficulties? Okay, so far those that are signing in here indicating they're seeing it, so
I'll try downloading it here and see what happens.
okay. And actually, in the meantime, I forgot, by default, this thing has audio here. I may actually mute folks initially, so go ahead and type in the chat window if you want to indicate anything else. But now I got to figure out how to do this. Actually, I think I heard. Did I hear you on the line, Joe? Yeah. Do you remember how do I do a global one, or do I just have to hit everybody individually? There it is. I see the button. Hopefully it doesn't mute me too. There we go. Okay, so if you want to be unmuted, just send me a text through the chat window there. Okay, so let's see. Okay, so what I was going to comment on is particularly when we're talking about treatment means is typically we end up with means of what are commonly termed last observation carried forward data or observed cases data, often abbreviated LOCF or OC. So if you're not used to using it, LOCF or last observation carried forward is often used in intent to treat analyses where they want to include either all randomized patients or maybe all patients that were randomized and received treatment and maybe had one post-baseline sampling. The intent to treat population varies, but to include all patients in the presence of dropouts, the strategy is often to take whatever was the last observed value for that patient and use that as part of the summary statistic, whether it be a mean or whatever else, in order to do the analyses, as opposed to observed cases, which is pretty much what it sounds like. It's just taking only the patients for whom you have observations at a particular observation time and taking and summarizing that. Uh, and and when we get data from the literature, you'll often get one or the other in a given paper. Also within a paper, you may get some mix of the two. Uh, just to complicate things, often endpoint will get reported as what amounts to LOCF, whereas any longitudinal data that might be presented in plots and such is often observed cases. So trying to decide which to use, whether to use either, and so on can be an issue. And in particular, both types of statistics are potentially biased estimates of what we might call as treated outcomes. By as treated, I mean if everybody actually took all of the medications and you were to take a mean of that, so that you actually knew what would happen if they were all actually treated with the assigned medication. Well, neither one of those types of statistics, LOCF or OC, is necessarily a good representation of that. And in particular, they have the potential for it to be biased in cases where the assigned treatment actually affects the dropout behavior. And in the other context where it can make a difference is if the measured quantity systematically changes with time in some fashion. So in either case, either one of those can be a sort of a misrepresentation of the as treated outcomes. Okay, looks like Dana's okay now. That's good. Okay. So now, on the other hand, LOCF statistics are probably the most commonly reported, particularly for endpoint, and maybe the only values available. The end result is in many cases you don't have a lot of choice, and you're kind of stuck with dealing with these things, but should be aware of the potential biases. In cases where you actually have both reported, which unfortunately is somewhat rare, it is possible to impute one from the other under some fairly strong assumptions. So, for example, if you actually assume that the assigned treatment does not affect the dropout behavior, you can impute LOCF from OC and vice versa, and from both you could impute as treated under that assumption. So actually you could do that whether you have the data, whether you have both reported or not. But the nice thing about having both is you could actually, to some degree, test that assumption by, say, imputing LOCF from OC and then seeing if the imputed or predicted value is comparable to the observed, or if there's some systematic difference. And if there is some difference, it would indicate that that chances are the assigned treatment does have some impact on the dropout behavior. Okay, but I'm not actually going to go into any further details there other than to indicate that it is a potential issue. Okay, so the main topic I wanted to get into then was to talk about combining summary and individual data. This is something that you may want to do in order to, for a couple of reasons. One is your main interest may actually be in the analyzing the individual data, but you'd like to gain some strength, maybe some strength of information, maybe some additional information about comparators, and bring that into the analysis to try and make some inferences, say about how a new agent compares to marketed things, but maybe you didn't do an active control for that marketed agent in your study. But you'd still like to make some indirect inferences about that. So you may want to bring in that summary data from that. Another reason where you may want to bring in individual data is you've heard in this class earlier about ecological bias that can result when using uh, meta-analysis of summary data. In other words, it looking at the influence of different covariates could mislead you if you try to interpret uh, those covariate effects on aggregate data as inferences about individuals. So individual data will provide you with will provide you with an unbiased or at least less biased characterization of the influence of those covariates on individual data. So so it helps to some degree obviate that particular problem, assuming you have enough individual data that's informative about that particular covariate effect. Okay, so how might we go about doing it? There's two methods I mentioned here. One is a simultaneous analysis of the summary and the individual data. And the modeling approach that I had presented to you for modeling longitudinal data can also be used to simultaneously model the summary and individual data. If you recall, the way we sort of developed that particular methodology is we started out by conceptualizing the data in terms of a model of individual outcomes, and then we adapted it to be descriptive of the summary data. So it makes sense then to simply use the initial individual data model that you started for individuals, and then you've got that modification to deal with the aggregate data, and you just combine the whole thing in that fashion. And in fact, that's really how we ended up coming up with the specifics of that methodology. We weren't even really thinking so much about the longitudinal data problem at the time. We were actually focusing on how to bring together summary and individual data, particularly longitudinal summary and individual data, and came up with that methodology, and realized in the process we also had dealt with the longitudinal data problem along with it. So that's one approach. Another way you could think about the problem is to deal with it sequentially. Uh, we could actually take advantage of the Bayesian machinery that we've been using for modeling the data here. You could model, you could do this sequentially where you might initially develop a model based upon the summary data. So for example, we did your previous hands-on example looking at ADAS-Cog for donepezil and placebo. Well, perhaps you might have developed that model, and once you have that, you could use the results, in particular our posterior samples, or actually our MCMC samples for those parameters. You could take those, approximate the distributions that you get from there with parametric distributions that could use as part of another analysis, and then use those distributions as prior distributions for a subsequent analysis of the individual data. So that's another perfectly reasonable strategy for doing it, and would be particularly reasonable in the case where maybe you sort of already had a model on the shelf. perhaps you'd been working in that particular therapeutic area, you had done a model-based meta-analysis in the past, you felt that that particular model was still relevant to individual data, so you could take the results from the previous analysis and use that to construct those prior distributions for analysis of the new data as it becomes available. So either approaches would be a reasonable strategy for dealing with this. The one we're going to focus on today will be the first one, which is the simultaneous approach. And to do that, what I'm going to do is what I actually labeled here as a hands-on problem. I'm actually going to do as a demo here for today. So it's an example what's going to be based upon the same ADAS-COG example we did before. So recall you had an example that was done as hands-on problem 5, that was contained in a folder that was called ADAS-COG hands-on. Well, we're going to do a variation on that. We're actually going to extend that by incorporating some individual level data. So as you see here, we're going to extend problem 5 by adding individual patient data from a simulated dose response trial for a new drug we'll call Metupazil. And we're going to simultaneously analyze that individual patient data from that trial with the same summary data we used back in problem 5. And I just comment here in one, one of the reasons you may want to do that is you want to enhance the analysis of your Metupazil dose response by borrowing information from prior data. In addition, it should be able to make your comparative inferences about, particularly between Metupazil and Donepezil, more precise. So the data we're going to work with here, we've got post-baseline sample means and sample variances for ADAS-COG change from baseline from published sources. So that's the same data we did back in problem 5. And since it's been a while here, maybe we should take a quick peek to remind ourselves what we were dealing with here. Okay, so we had data then from 12 studies containing 24 treatment arms, bunch of sample means, somewhat fewer sample variances in there. And it all represented trials that involved Donepezil. And this is just giving you some quick views here of the data here. The left-hand panels, each panel corresponds to a different trial. The points there are all observed mean ADAS-COG change from baseline values in here. And well, you can see the various time courses over in the studies all had somewhat different durations in here. You can see the colors correspond to different Donepezil doses, black in particular being placebo outcomes, and the right-hand side are the sample standard deviations. I think that was all the data in there. The model, actually, was there more I wanted to say? No, we'll jump into the model we're going to be using is going to be the same as the one that we did for that, except now we are going to be incorporating the individual patient data as part of this. So recall again, we started out by first conceptualizing the problem in terms of individual patients, and then modified it for the summary statistics. So we'll actually be using the individual patient data model directly in this case for the individual data. So just remind you, we're looking at ADAS-COG change from baseline and the ith occasion, jth patient, and case study. So our ADAS-COG change from baseline, we just had a normal residual variation with some mean that can vary by occasion, patient, and study. We also have our variance term here. I've got a subscript K, so we're allowing for intertrial variation and the residual variation. That mean here, recall we have sort of a disease progression component that's just a straight line with a, in this case, it's going to be a patient-specific slope. A placebo outcome that we just model is basically just a constant change from baseline here. Again, that is patient-specific. And then finally, a drug effect component in here. And for our drug effect, recall we had this exponential sort of model here where we've got our djk over dref. I think I'm going to double check. We'll get to it here in a second, but I think the dref was 10 for donepezil. And since, well, that's right, we're going to have two active drugs. I don't remember what we're using. I'll look in a minute for metupezil. And then we've got this sort of Emax model describing time. Let's see. Well, yeah. Oh, I'm sorry. DREF, I guess, was 5 for donepezil here. Let's see what else we got. We've got our maximal drug effect with it has a what do we have? An inter-trial variation on that. No inter-individual variation. Again, our e-placebo, we've got inter-individual variation on that as well as inter-trial. And then for the slope over here, we've got our inter-individual variation and our inter-trial variation on that. And then finally, inter-trial variation on our sample variance, or our, not our sample variance, our whatever, our residual variance term here. And recall, this is how we adapted it then for dealing with the our summary statistics. We have both the both our change from baseline, our mean change from baseline, as well as our sample variance for that change from baseline in here. Again, we still have the normal distribution then, except that it's sample size adjusted. And then for our sample variance, that's going to be a gamma involving our sample sizes again, and we have to generate this marginal variance term in here, which involved doing the, recall we had to go through the process of dealing with the partial derivatives of part of our model in here. The end result, we end up with this sigma squared here, marginal. We've got a term which is related to the square of time, and then we have another square of time multiplying our where we got here, I guess that's our inter-individual variance for our slope, our inter-individual variance for our placebo outcome, and our residual variance term in here, all contributing to that. And then wherever we had the inter-individual variance, it becomes an inter-arm variance by adjusting for sample size. Okay, so that's exactly the model we're doing. The big difference again is that we're going to be implementing both this form of the model for our sample statistics as well as this form of the model where we're going to be dealing with just the individual change from baseline value. Of course, in the case of individual data, there is no sample variance to talk about. Okay, let's get back to the specifics here and for the combined case, where'd it go? There we go. Okay, so that's our making reference to what we talked about the model now and the original sample statistics that we had before, but now we also have our individual data from a metupezil dose response trial where we have placebo as so we've got a placebo control, also an active control. In this case, so I guess in this case it's donepezil 5 milligrams per day. And then we have 3 different dose levels of metupezil in here. You can see the sample sizes there. We've got some longitudinal data, so we've got post-baseline observations at 6, 12, 18, and 24 weeks that we're going to have here. So we're going to be constructing our model for that, or actually we're really going to be extending the model we already have for that. Just to give you an idea what kind of data we're looking at, here's our individual level data for the different treatments. So here you've got our 2 control treatments, placebo and donepezil. Again, these are plotted all as ADAS-Cog change from baseline versus time. You can see they bounce around in various different ways here. Ditto for a couple of the metupezil treatments. I guess I should have given you some summary stats to sort of see the sort of mean impact here. But there is, I did, the simulated case is such that metupezil does have some effect here. Okay, so how do we make use of this? The main differences between what we did before and what we'll do here is frankly kind of bookkeeping stuff to keep track of where the sample sizes are relevant and where we're dealing with individual data versus summary data. So let's take a look at that. Let's go ahead and move that out of the way. Okay, so that's contained in the folder here, ADAS-Cog2 hands-on. Okay, let's go ahead and open up the model itself. Oops, it's not quite what I wanted. There we go. Okay. Now, if you actually go back and look at the ADAS-Cog hands-on and look at that model, you'll find a lot of similarities. They are very close to each other. In fact, some of the sections are essentially identical. In fact, maybe it'd even be instructive to go ahead and open that up just to illustrate some of that. Let's see, ADAS-Cog hands-on. Let's see, let me pop that out here. Oh, shrunk back down. Okay. Okay. So recall we've got a couple of loops here, one that loops over studies, one that loops over what I labeled as units. And the reason I had used the word units before is I was kind of trying to look for something that was more general than arm, because now our units could be either treatment arms or individual patients in here. So that's either way, we end up with these 2 loops there, and then there'll be a third loop that's going over the observations. And if you look at this, you'll see some of these are identical. So the right-hand side is what we used for the aggregate data only. Left-hand side is for the combination. So, and notice that for the inter-trial variation, they are completely identical. I believe they might be identical also. Sorry, that moved too fast. There we go. For our loop over units, I think that's also, yeah, that's identical. Though notice that in these, there's a place where we adjust the precision for For the sample size, well, of course, the sample size for individual patient data is just 1. So we wouldn't have had to have made that adjustment, but it doesn't hurt. So we can actually leave the code the same without having to deal with it. So that's still identical. But in the case, of course, for the case where it is a sample where we're going to be dealing with the aggregate data, we did need to do that, and the n will be something greater than 1, of course. And this does the appropriate adjustment in there. Then the next is we're going to have to deal with some differences when we start looking now at the level of the likelihood, where we start looking over the individual observations. So in one case, the observation is going to be sample mean or a sample variance. In the other case, it's going to be it's only going to be the individual change from baseline values, and we have to treat those a little bit differently. So what we'll see is there will actually be one loop here in the previous code here. You'll see I looped over all of the observations because they were all summary data in there. And that loop is going to be identical to one that I have here for our combination, where I'm going to loop over only the summary data first. So I'm actually going to be breaking the data up sort of into two pieces, if you like. The initial part's going to be containing only the sample means and variances, and the next part will only contain the individual data in here. So, but this loop where we go over the summary data is going to be pretty much identical. In fact, it probably is identical. Well, I need to say almost identical to what we did before. I also have to account for the fact that we're now introducing another drug into the mix here. Before we only had to worry about, there it goes. We only had to worry about donepezil before, because we have, basically you had either donepezil or placebo, and placebo you can generalize from donepezil by just making the dose 0. In the case we were looking at, here it's going to be, we also have to account for that. We have two different drugs, so we're going to have to include more than one kind. We're going to have different drug effect parameters for the two different drugs, so we do need to account for that. So that's about the only difference you're going to see in this particular loop. The first parts of the loops are identical. I guess you're having trouble seeing the right, but it doesn't make much difference because they're not really different here for the first few lines. Where things get a bit different here is when we get to the drug effect. Where'd we go here? Oh, I'm forgetting what's here. Here we go. Actually, I overcomplicated it. I see here. I did this. I created this extra complication, I think, because I actually need to double check what I did in the R script, but I believe I had set the drug indicator to 0 for the placebo. And yes, I did. So this is just a trick here to set this thing that I called I drug to 1 in the case where it's placebo, so that it doesn't cause grief when it tries to use the drug indicator as an index for the variances. That was actually silly. I could have actually done this back in the R script, and it would have been simpler. That's essentially what I did before, when we only had one. I also don't really need this, which is basically becomes 0 in the case where the treatment is placebo. So it zeroes out the E drug. Well, it would have been zeroed out anyway because the dose would have been 0. So in hindsight, I made this more complicated than it need to be. I could have actually just used the same code I did here, and just for the placebo arm, just given it either one of the other drug indicators, and it would have gone along its merry way with no problem because the dose would have been 0 and it would have just set drug to 0. So if you wanted to simplify the code I did, you could get rid of some of this nonsense. The only other thing you need in here is, since we've got 2 different active treatments, we now have to have, the dose ref will depend upon which drug it is, the all the parameters here, the gamma, the what do we got here? The E delta, the ET50, uh, all of those things are potentially drug specific in here. I didn't necessarily want to assume they would be the same for both drugs. So that's the complication we had, whereas before we only had one drug to worry about, so you don't see all of those subscripts on these. Let's see. Otherwise, it's the same story in here. You've got to calculate this tau marginal. Again, is just the reciprocal of that sigma squared marginal in here. So that takes care of that, and that's used as part of the, well, notice that then gets used to calculate this parameter here, this b-var, which is used inside the likelihood for sample variance. By the way, all that's going to go away. We won't even need to calculate that for the individual data. Okay, so again, other than the drug-specific elements of this loop is identical to the loop we had over all the observations from problem 5. Now, if we scoot on down, get past all of that, where are we going here? There we go. Here what I did is I set up the data again as sort of the summary data was stacked on top of the individual data. So now I'm going to do a loop that's going to go from basically the end of the summary data to the end of all the data. In other words, it's going to be going through all of the individual data within this loop. And this just becomes what's essentially a simplification of what we did for the summary data, because now all we have is the observed. I notice it still, I forgot to get rid of that little bit. That's no longer a sample mean, because now we're just looking at the individual observation for our ADAS-Cog change from baseline. We have no sample variance to worry about. As a result, we no longer have to worry about that marginal variance term any longer. That's no longer relevant. So we jump right to our ADAS-Cog mean model here, and everything else gets a lot simpler. So all of this is largely a replication of what we saw in the previous loop, but without having the extra complications for dealing with the summary statistics. And then when we get down to our prior distributions, there we go. Just compare that to what we had before. Again, they're very similar. The only real difference that occurs here is where we only had one drug for which we had to calculate the basic parameters here. And just remind you, I had used that truncated Emacs reparameterization, and I'm doing it again here, but now I'm doing it twice because I have 2 different drugs. You can see it says for I equals 1 to n drugs. Well, n drug is just 2, so it's donepezil and metupezil here. And I'm pretty sure I did the coding as 1 for donepezil and 2 for metupezil. So this is identical to what we had before, except it's doing it twice, basically. So you end up introducing subscripts on all of these parameters that you didn't need before. Otherwise, it's identical. So as I say, we basically, when we solved the longitudinal data problem, or at least came up with a reasonable approximation for it, we also did the same for the problem of combining individual and summary data. So this is what we're going to apply. There's a little bit of bookkeeping, additional bookkeeping that happens in the R script. Let me pull that up. Make sure I'm in the right thing here. Yeah. Okay, why is it? Okay. Okay, so again, this is pretty much taking the ADAS COG hands-on code, making a few changes. Obviously, I had to change the name here. And most of it is buried around in a little bit of data management here. So in addition to pulling in the donepezil data that we had used before, there's a new data set here called matupezil.csv. I guess maybe I can pull that up here. Okay, and you can see it's a fairly simple one. We've just got an ID variable that's different for each individual patient. We've got a week indicator here. So again, you can see the samples we're taking at 6, 12, 18, and 24 weeks. I think I was lazy. I don't think I simulated any dropouts in this example, so it's not entirely realistic there. The drug name, which in this case is either going to be placebo, donepezil, or matupezil. I guess sort of redundant with that is a drug indicator, which is 0, 1, or 2 for, again, placebo, donepezil, or matupezil. This DTOT is the daily dose here. And finally, the ADAS here is actually ADAS COG change from baseline. So that's all there is to the data set itself. So you can see that's pulled in with just a read CSV statement. And where are we going here? So there are things I added in order to make the data sets have the same structure in here. So for example, for N TRT is the sample size. These are the names that were used in the summary data set. So I generated that, where of course the sample sizes are all 1. PY indicated the publication year. In this case, it's kind of obviously made up, but I have 2008 here. Stat anal is an indicator for which type of statistics we're talking about. In our case, this is just observed values, so I just substitute that in there. As before, we go ahead and create sequential indices for study, for treatment arm, and of course, treatment arm here is also going to be synonymous for also each individual gets such a unit ID in this case. Where are we going? Oops, just did something I probably didn't want to do. There we go. Yeah, what am I doing? I'm generating also some other indicators for units. Study age, I don't know why I bothered. I didn't actually include that as a covariate, so we won't worry about that. Some drug names and so on. So most of that, again, is bookkeeping to allow us to create the data set we need in here. Recall we had to indicate how many summary data observations there were, how many individual patient observations there were, and so on in here. And after that, the code is, I believe, it's almost identical. For the initial estimates, I now had to include 2 gammas, 2 E stars, and 2 Bs in here, a separate one for each active drug that's in here. And I think after that, it is identical, I believe, from there on out is what we did before, except when you get down to the plots, since I created separate plots for the summary stats and for the individual patients in here. Now, This one, if you actually, the version you've probably got, I had been monkeying with this a bit today. The version you've got probably had 3 chains of 10,000 iterations each with 5,000 burn-in, I believe, and thinning of 5. And I actually did such a run with this. Actually, before I even take a look at the results here, should check here if there's any comments or questions. In fact, why don't I could even unmute you guys for that here. Okay, did it? Okay, it did. Anyway, any comments or questions on the setup so far before we take a look at the results? Guess not. Ominously quiet here. Probably put you all to sleep by now. Okay, let me go ahead and I'm going to mute you again here. So let's take a look at what happens when you actually run this. Actually, let's go ahead and take a look at the results I had when I only did the 3 chains of 10,000 each. And we see here, it depends on which parameter you look at. Some of them don't look too bad, though. I'm a little bothered here by the sort of this, you can sort of see things, the green and black are sort of running above the red patch here. So the chains aren't quite coalescing there. You see that with B1 here too. And E delta is kind of noisy here. E stars are both kind of not looking as pretty as I might like. And a couple of our variances here, the omegas for placebo study and omega drug are not looking too hot. We're not seeing gross convergence problems, but it's pretty evident that the amount of autocorrelation is severe enough that we probably don't have enough samples here to make good inferences. And omega E placebo unit here, essentially the inter-individual standard deviation for the E placebo component, is particularly ugly. Again, it's not super gross convergence problems, but there just aren't enough samples there to make any reliable inferences about that parameter at least. And it might not bode well for other inferences. So that suggests either we need to revise either the model, the parameterization of the model, or we just need to do more samples. If we look at, close that, if we take a look at our summary here, get a little bigger in here and take a look at particularly at our effective N for this, we can sort of see where some of these things crop up. Where's that omega E placebo here? Yeah, like you can see here for the one, we've got an effective N of like only less than 50. I think that's the worst of them, but there are several others that are less than 100, which is, again, it's a bit small for doing reliable inferences. So yeah, my immediate reaction is it's not disastrous. So I'd probably be happy with just doing a longer run. Just to give you some idea too of the run times to do, let's see, this was about, it was about 10 minutes to do the run of 3 by 10,000 on my MacBook here. So I said, okay, well, let's go ahead and just multiply by 10. We'll do 100,000, 3 chains of 100,000 and see where we end up. Before actually taking a look at our parameter estimates and making use of those. That was this run up here. Oops, I just did something I didn't want to do. There we go. Where do we go here? Okay. I was looking at the wrong one. Okay, here we go. So let's start with the summary table here. And let's first of all look at our problem cases here, particularly these guys. So we can see we've gotten up to a little better than 300 and 400. May not be perfect. I'd rather see thousands, but for for a variance related parameter that I'm probably not going to focus on for inferences, I'll probably live with that. Now this run, so this was 3 by 100,000. In fact, you can see that in the code here. So I did 3 chains, 100,000 each, did a burn-in of 20,000 and kept every 50th. So the end result is you have like 4,800 samples total to play with when you're done. If we take a look at the history plots here. Okay, you can see we're definitely more fuzzy caterpillarish here than we were before. Ditto here. Okay, remember one of the problem ones was on top. It's definitely looking better, although not entirely perfect there. You can still, the autocorrelation is still pretty evident in there. But again, if I'm not making inferences directly on that, I probably end up living with this particular run. Again, you see the issues with that, also the one on that. And in general, what we see is that placebo effect component seems to be struggling a bit. Just to give you some idea of other things, another interesting clue here of a potential issue is I can see at least one parameter that for which the data wasn't very informative. It looks like we have limited information in the data about the what the time course looks like for, I think this is for the Metupazil. I'll have to double, I think that's what the number 2 is. Notice what this looks like. You've got something that's almost uniform 0 to 100. A little more weight early than later. And I think the prior, let's take a look at our prior on that. I believe the prior was 0 to 100 for that. And it is. There's a uniform 0 100. So that says, okay, it looks like the data is not very informative about that parameter at all, which is, so it's saying it can't estimate that particular component. And keep in mind that parameter is related to what we call the ET50. In fact, somewhere, did I plot the ET50? Yeah, it is here. Of course, it's inversely related to the ET50, so it's a little harder to see. Now, I guess it is saying that it looks like it's fairly low, but that's about all it knows. It can tell that basically it's looking like the effect comes on fairly quickly, is basically what that's saying. And it knows that, but it can't tell you with precision how quickly. And the fits, not a whole lot to say when we look at the raw fits. They don't, other than being able to say something about how good or bad they are, it's not very good for probably what we want to use the model for, which is to make comparative inferences about Metupazil and Donepezil and placebo. But again, it tells us something about the fits. Okay, what do we got? These are the population predictions. And here you can look at the individual predictions for our individual data in here, so you can get some idea of the extent to which we seem to have been able to describe the results here. I'll just sort of scan through those. Back to our Donepezil. And then, oh, you know what? I'll bet I mislabeled. I think I'm actually into the population. In fact, I know I'm into the population predictions, and I did not change the labeling on the graphs for it. Need to fix that. And then it's got various diagnostics here. About the only thing that jumps out as I look at these are basically comparing the distributions we used in the model to, which I think are almost all normals in this case, to the empirical distributions. And things are looking okay until we get to that, which probably tells us one of the reasons why we're having trouble with e-placebo. Is I recall, and part of this, frankly, is because we know we were using an oversimplified model to describe the placebo outcome in this case. So that's part of the reason. It also probably reflects one of the reasons why in the original real data, I had been using a t-distribution to deal with the tails. But I think part of this is just simply a systematic problem with the fact that we're approximating a time varying placebo distribution with a placebo effect with just a constant. Okay, we won't go through all of those. Okay, so we've got a model. Let's for now, other than we've got maybe at least one problem that we're looking at with the placebo effect component here. Let's say we've got a functional model here. And the question is, okay, well, we never really set out at the beginning here what the objectives of the analysis were, but I think you could imply that, again, the interest here would be if we're developing a new compound and we're going into a marketplace where we might be viewing donepezil as a standard of care, or at least an important comparator, we're going to want to understand how our new compound is performing relative to that. Maybe try and identify what, if any, doses are equivalent to or superior to the donepezil in order to assess, one, what dose should we select for further development, and two, whether any dose is likely to perform acceptably, be adequate to actually support marketing of such a compound, which is actually going to lead me to where I'm going to take you for the final exam on this. And some of you missed the beginning here, but my intention here will be to actually have you guys use the results of this analysis to make some inferences about metuprazole. And what I'll do is I haven't written it up. I'll write up a set of whatever questions or specifications for what I want you to do for that final exam. But the core of it will be to do some posterior simulations suitable for making inferences about the comparisons of metuprazole to both placebo and donepezil, and to provide those results, probably both in graphical as well as some numerical statements as part of that. So, and I will write up something and send it out. I think I should be able to get that out the door by the end of the week here. And I guess that'll be due, I don't know, I guess 2 weeks after I post it is probably acceptable for completing that. Let's see if there was more I wanted to say about this. I don't think I had any more in my slides, but let's double check. Where did the slide? Oh, I slid them over there. No. Okay, well, let me again check in with you guys and see if there's any comments or questions that you have about this, or anything else for that matter. I guess this will be our last session, and it looks like we're actually going to be ending this one just in a few minutes here. Probably won't take it. Well, in fact, I know we're not going to take it all the way to 4. Oh, and you're unmuted if you just wanted to make the question verbal. Okay, the question I've got here is at what point do I stop increasing the number of runs? I assume by number of runs, you're probably talking about number of iterations before I call it a day, assuming you're still not getting the nice fuzzies here. Um, well, I don't know that I have a magic number here, but if for instance, in the particular example I did here, okay, so let's say that 3 by 100,000 there, if at that point it was obvious that I wasn't going to get adequate convergence, and again, I'll try and make a sort of the distinction between convergence and simply not having enough samples for inference. So it would make a difference. So for example, if say after 100,000, I saw something that looked kind of like it did after the 10,000, there I would have to make sort of a calculation about the trade-off between the time that it was going to take and whether it was worth doing, or whether at that point it's worth taking a much closer look at the model, and either the model or its parameterization, uh, and and just decide, okay, is this just a problem with the Gibbs sampling, or have I actually really got a model problem that I need to diagnose? And we'd be getting close to that with the 100,000. The run with 3 chains of 100,000 on my laptop here took about 90 minutes, about an hour and a half. So that's not necessarily prohibitive. Lord knows I've done non-mem runs that have taken a whole lot longer than that. So I could conceivably consider moving it on up to maybe 1 million or something like that per chain, particularly if I do them in parallel on different machines or different cores. But I'd have to have a pretty good inkling that I was likely to have success. So I would be looking at the history plots to see, okay, are they at least showing signs that they're describing the same distribution, that they're not completely disjoint. Because if I see different chains are pretty much completely separated, then I'm definitely going to start looking at the model and the model parameterization, because that indicates, or the methodology I'm using for fitting it, because that indicates a problem that's simply doing more samples. It's not going to solve it. But if they're mixing and I really kind of believe that the model's appropriate, I might just go ahead and do the longer run. Again, there's some upper limit on that where it just becomes impractical. And that's going to depend upon the context. So I don't think I've given you a very clean answer, but I hope I've given you at least some clues on maybe some of the things you might want to be considering when you do it. As I say, if I really think the Gibbs sampler is the stinker, I might start looking at things like there's some other softwares out there. I don't recall if I mentioned it in this class, but Andrew Gelman and his group have developed a new package called STAN, S-T-A-N, which uses a different sampler, which he claims does better in a number of contexts. So that'd be an example where I might say, okay, let's see if we can port it to that and see if it does any better there, for example. So that'd be another direction. Anything else? Okay, well, And this is, I guess, our last session. I hope you find it helpful. I certainly enjoyed the chance to telling you about this stuff, and and look forward to seeing you in other contexts along the way. Uh, certainly feel free to ask questions as you try to apply these methodologies. Assuming there are things I can answer in reasonable amounts of time, that will be fine. You've got my email, so you can go ahead and pose those questions. Um, let's see. Got the question: will there be additional courses building on this one? I don't have any specifics in the works right now that go after model-based meta-analysis. No. Um, some of the newer courses we've been adding on go in a little bit different direction. Uh, Recently, Mark in particular has put together one focusing on simulations for supporting strategic decision making in drug development. So that includes, going further with the kinds of things we talk about here in population simulations, but also goes into far more detail around clinical trial simulations, for example. So that's the newest one that we're adding to the hopper. Trying to think if there's others. No, I mean we occasionally brainstorm on new courses, but again, nothing that's a direct sequel to this one. Okay, well, I will say farewell for now. Again, I look forward to seeing you all in other contexts in the future. Again, I will post the final exam, and again, for those of you that want to undertake it, I guess I'll be looking forward to taking a look at those in a couple of weeks. So, goodbye for now.
Thank you, Bill.
Okay, thank you.